Hello everyone, my name is Zhipin. It's an honor to have the opportunity to address such a distinguished audience. The subject of my presentation is asynchronous distributed learning with robustness to malicious guidance. Large distributed learning is emerging to be an attractive solution to make use of the increasing amount of data today. In this setting, devices could build the local model gradients to a central server. The central server then gathers gradients from the workers and combines these gradients using aggregation methods, such as Cardam, to train a new global model update. Finally, the server broadcasts the new global model update to every worker for computing new gradients. Distributed learning can be categorized into two types: synchronous distributed learning and asynchronous distributed learning. On the one hand, synchronous distributed learning requires the parameter server to wait for a quorum of workers before generating the C-aggregation model gradient. Asynchronous distributed learning, on the other hand, enables the server to update the global model as soon as worker responds. When networks are asynchronous, exhibiting heterogeneous communication delays, asynchronous distributed learning is proved to be generally faster than synchronous distributed learning. Unfortunately, the distributed nature of distributed learning results in its vulnerability in adversarial attacks. As shown in the graph, the malicious devices can easily attack the global model by sending malicious gradients. Our paper focuses on three types of adversarial attacks, namely untargeted model poisoning attack, targeted model poisoning attack, and lagging attack. Untargeted model poisoning attack modifies the messages transmitted from the client to the central server, resulting in a model performance deterioration or the failure of model training. Targeted model poisoning attack exploits the lack of transparency in the client updates to induce the jointly trained model to misclassify a set of chosen inputs. Lagging attack, on the other hand, results from the variety in latency and system configuration and availability issues at edge devices. Distributed learning with robustness to model poisoning attack has gained significant interest in recent years. Most of the existing aggregation methods extend SGD to defend against untargeted model poisoning attack. Asynchronous distributed learning methods are also proposed to address stragglers and dropouts. However, existing robust asynchronous distributed learning methods cannot defend against targeted model poisoning attack effectively. Therefore, an asynchronous distributed learning framework that timely detects and moves malicious model updates is still a significant roadblock to asynchronous distributed learning's practical deployment. Since VAE is effective in anomaly model detection, we propose a VAE-based method to detect and move malicious model gradients. Based on VAE, a state-of-the-art malicious model update detection algorithm, Spectre significantly outperforms our traditional algorithms. However, Spectre is a synchronous distributed learning method and is vulnerable to lagging attack. In the asynchronous training process, model gradients are hard to aggregate due to the lack of synchrony. To apply VAE to asynchronous training settings, we propose to detect the malicious model updates based on VAE and then use asynchronous distributed learning methods to process the received model gradients. VAE is a model with the encoder-decoder architecture. The encoder module projects original variables to the low-dimensional embeddings. The decoder module then reconstructs the original variables from these embeddings. As shown in the figure, the reconstruction errors of abnormal cases will be much larger than that of normal cases. We make the following assumptions about the distributed system. Assumption 1. bounded device delay. For our work, we assume that the maximum delay of radius received from a single device is bounded. We simulate the asynchronous setting by drawing random delay from a uniform distribution in the range of 0 to k subscript w, where k sub w is the maximum device delay. Assumption 2. The server is fully trusted. The server plays a vital role in detecting and excluding malicious local model updates from devices. If the server is compromised, the aggregated model will be vulnerable to adversarial attacks. Assumption 3. No malicious devices in the beginning. Devices will be vulnerable but not compromised when they first participate in the distributed network. It takes some time for adversaries to compromise devices, leaving sufficient time to generate the validation dataset. As mentioned above, the devices in distributed learning networks are often compromised before the model training starts, so there is no time to train the detection models in advance. We use novel asynchronous distributed learning methods in the first several apertures to generate enough training data for VAE, and then use VAE to enhance the normal learning methods in the following apertures. Since the VAE-based model is supervised, we need to train the model in parallel. We employ normal asynchronous distributed learning methods to generate enough data to train the anomaly detection model. We use the anomaly detection model in each communication round of the model training process to detect malicious model updates. As mentioned above, the reconstruction error of malicious updates is much higher than that of benign ones. The reconstruction error is the key to detect malicious updates. To avoid the curse of dimensionality, as Spectre does, we employ a surrogate factor generated by randomly sampling the model update factor. As shown in the experiment, random sampling is highly efficient. The server generates the surrogate factors of local model. We also use normal asynchronous distributed learning methods to generate the global model update sent to clients. In other communication rounds, we also generate surrogate factors. We use the trained VAE to compute the reconstruction error of the surrogate factor. Unlike Spectre has done, we set the detection threshold as a fixed value due to the majority of malicious devices. The updates with reconstruction errors higher than the threshold are considered malicious updates and are excluded from the following process. After excluding the malicious updates, the remaining updates are processed by normal asynchronous distributed learning methods such as Zeno purpose to generate the global model update sent to the clients. Therefore, our method's convergence property is the same as the asynchronous distributed learning methods that we use. Since the existing asynchronous distributed learning methods are vulnerable to targeted model poisoning attack, cannot employ normal asynchronous distributed learning methods to generate enough labeled data to train the anomaly detection model. We prepare the validation dataset for VAE. The validation dataset used for training VAE models can be structured in many ways. It can be a separate validation dataset offered by a trusted third party. The validation dataset is small and different from the training dataset. The validation dataset is only used to train VAE models and validate gradients in Zeno++ and won't be directly used in the training process. Let's move on to experimental settings. In our paper, we designed 3 experiments. First, we evaluate the robustness of async VAE B1 to untitled model poisoning attack in the phishing list dataset. Second, we evaluate async B1's robustness to lagging attack in the phishing list dataset. Third, we evaluate async VAE B2's robustness to backdoor attack on the phishing list dataset. We conduct experiments on the benchmark phishing list. We repeat each experiment 10 times and take the average. Each experiment is composed of 200 approaches. While each approach is a full pass of the training dataset, we simulate the asynchronous setting by drawing random delay from a uniform distribution in the range of 0 to k sub w, where k sub w is the maximum device delay. In the experiments, the number of malicious devices Q can be greater than the majority of the total number of devices. The number of total devices in the experiments is 10. The phishing list serves a similar benchmark to the popular list dataset. The phishing list image classification dataset consists of a training dataset of 60,000 images and a test dataset of 10,000 images. We use a convolutional narrow network with 4 convolutional layers followed by 2 fully connected layers. We randomly extracted 3,000 of 60,000 images for training as the validation set for our methods. We assume that the proportion of malicious gradients received by the server is the same as that of malicious devices. We distribute the remaining images among 10 workers, so the bounds of cardam do not hold when Q is larger than 4. In the first experiment, we evaluate our method's robustness to untitled model poisoning attack. We consider 3 types of attacks in our experiment, including same-value attack, additive noise attack, and sign flipping attack. Same-value attack sets the local gradients as the same values. A sign flipping attack flips the sign of the local model gradients. Additive noise attack adds Gaussian noise to the local model gradients. We evaluate our method's robustness to untitled model poisoning attack into scenarios where 20% and 60% of selected clients are malicious respectively. In the experiments, our proposed method uses the async VAE framework and uses zero purpose to process the remaining gradients after detecting and removing malicious gradients. Let's take additive noise attack as an example. As shown in the figure, our method achieves the best performance in the phishing list dataset on the additive noise attack. Our method converges faster than other baselines and achieves much more stable top 5 accuracy. So the performance of cardam is even worse than Async SGD without defense ability. The filter in cardam leverages the robustness of cost functions, which seems not robust to additive noise attack. Our method and zero purpose perform much better than cardam. The top 1 accuracy and the top 5 accuracy of zero purpose decline about 15%, and the cost entropy of zero purpose rises about 2 in some approaches, which seems that the appropriated stochastic descent score used by zero purpose doesn't work well in these approaches. Our method uses VAE to detect and mitigate the impact of malicious gradients, which performs better than zero purpose in these approaches. In the second experiment, we evaluate our method's robustness to lagging attack into scenarios where devices have no response during the entire training process or in certain periods. We set a certain preparation of devices as malicious devices and show the performance of distributed learning methods or benchmarks in the left peak. As shown in the left peak, our method achieves the second best performance. Asynchronous SGD performs best while Cardam performs worst. The performance of Zeno++ gets worse when the dropout rate reaches 100%. Async VAE uses VAE to detect and remove malicious gradients, making its performance better than Zeno++ in these scenarios. Cardam is the only method with increasing accuracies and decreasing cross entropy as a dropout rate rises. The filter in Cardam leverages the robustness of cost functions, which seems robust to lagging attack. The poor performance of the other methods when the proportion of malicious devices increases may result from the worst model generation as the dropout rate increases. We also evaluate the performance of our method and the existing asynchronous distributed learning methods when devices are periodically non-responsive to the parameter server. At each approach, we randomly select a certain fraction of devices as non-contributing devices. Right peak shows the convergence performance for different proportion of periodically dropout devices. As shown in right peak, as the proportion of periodically dropout devices increases, our method will still converges well with slightly worse performance. Therefore, our method is robust to periodical lagging attack. Backdoor attack is a targeted monopoly attack. We evaluate our method's robustness to backdoor attacks in a scenario where 8 clients in fetching list are malicious. On the backdoor attack, the adversarial goal is to induce failure on targeted subtasks. For example, in image classification, the backdoor attack may aim to enforce the model classify images with the label cat as a label dog. For the text classification task, the adversary may aim to suggest a particular restaurant's name after observing the phrase "my favorite restaurant is." The naive approach that simply trains the model on backdoor inputs can easily break distributed learning. In the experiment, it simply trains its model on backdoor inputs. The training dataset includes a mix of correctly labeled inputs and backdoor inputs to induce misclassification. In the experiment, our method used async VAE to detect and exclude malicious model updates and use Heyuan purpose to process the remaining gradients. As shown in the fig, where 8 of all the clients are attackers, our method achieves the best performance on the fetching list dataset on the backdoor attack. The test accuracy of async VAE is highest, while its backdoor accuracy is the lowest. Cardam has low backdoor accuracy and low testing accuracy because the filter in Cardam misclassifies most of the gradients as malicious gradients. Sync SGD without any defense has high testing accuracy and high backdoor accuracy on the backdoor attack, which shows the effectiveness of backdoor attack. Zeno++ has the second best testing accuracy behind async VAE, but cannot defend against backdoor attack. In conclusion, our paper proposes a PA-based anomaly detection framework named Async-VAE, which detects and excludes malicious model updates sent by devices in distributed networks. After excluding malicious updates, we use normal asynchronous distributed learning methods such as zero-purpose to process the remaining gradients. A method can accurately detect and eliminate the impact of either targeted model poisoning attack, attack, and untargeted model poisoning attack. We conduct experiments on distributed learning benchmarks, and the results show that Async-VAE has a competitive performance compared to existing asynchronous distributed learning methods under these attacks. That's all. Thank you.